Okay, the next section is called the shear and moment diagrams. So as engineers, when we're designing structures, we want to know what the internal loadings are in these structures. So let's just use beams for our discussion. So suppose you have a beam, point A, and you have point B here, as well as point C, and we have some force like that, and there's an applied load, let's say, of force F1. And now what we're interested in is how do the shear force and normal force, as well as the bending moment, vary as we move along the length of the beam? So before I introduce how we go about determining that, I want to show you some of the convention that we use in terms of nomenclature. So convention for internal loading, nomenclature. And that just means variables. Fancy word for variables. So we'll definitely have to use the method of sections. So if I section it there, what I'll have is two parts of the beam. So here's the part on the left. I guess we should label this as AY and CY. So I'll have this force AY, and at the section part, I'll have this tensile force. And the convention is to name that tensile force with a variable n, and that means it's a normal force. And we also know that there's a shear force on that face of the beam, and we denote it with an arrow that looks like that, and we use a variable v. And this means it's the shear force. And it'll also have this internal moment, and we'll use the variable m. As you can see, I've assumed a specific direction for these internal loadings. So let's be consistent as a class. We'll always assume that the directions of those loads are as follows. Okay, so assume internal loads when exposed cause 1, tension. So that'll dictate the direction of your normal force. Normal force. You're going to assume that the shear force will cause clockwise rotation. And for the moment, moment will cause concave bending. So as long as we are all consistent with that, then the work that we do can be comparable, and it'll be easier to discuss it during the class. I think the best way to demonstrate the concepts of this section is just to do a problem. So let's say we're given this beam, and attached to one end is a thrust bearing, and attached at the other end is a journal bearing. So this is a thrust bearing, and this is a journal bearing. And that is 5,000 newtons. We'll call this point A, point B, and point C. And they also let us know that these dimensions are 2 meters, 2 meters. What we're required to find is they want to know how the internal loads vary along the beam. So how do the internal loads vary along the beam? So solution. The first step in solving this type of problem is you have to determine the reaction forces at the support. So determine reactions at the supports. So there's my beam. It's idealized. Here's point B, point C. So this thrust bearing prevents the beam from translating in the X and Y direction. We'll use that coordinate system. Therefore, I will have a reaction force in the X. I'll have a reaction force in the Y. The journal bearing prevents translation in the X and Y. Therefore, I will also have reactions in those directions. So the journal bearing allows freedom to move axially, but it prevents translation in the Y. So I will assume that I have a reaction CY, and of course I have to apply the external load 5,000 newtons, like that. So I apply my equations of equilibrium, and I get the following. Sum of the forces in the X is 0, so I have AX, that's equal to 0, so that was simple. Sum of the forces in the Y is 0, that would be AY minus 5,000 plus CY is equal to 0, and sum of the moment is equal to 0, and I get to choose a point. I'll choose point A. That gives me this moment arm times 5,000. That'll give me a negative moment. This moment arm times CY gives me a positive moment. So CY is equal to 2,500 newtons. I can substitute that in there, and that'll yield AY to be 2,500 newtons. So what we have now is then a beam A, B, and C with a reaction force here at 2,500 newtons, reaction force at C with the value of also 2,500 newtons, and a force of 5,000 newtons. So we've determined our reactions at the supports. Step 2. What we need to do now is express internal loads along the beam as a function of x. So what does that mean? We know that along the beam, there are internal loads, and it'll vary as it progresses over to the right. So we want to know shear force as a function of x, normal force as a function of x, and also moment as a function of x. In order to do this, we have to use the method of sections. Method of sections systematically. So this is how we do it. So I have my beam A, B, and C with 5,000 newtons and 2,500 and 2,500. In order to find these internal loadings as a function of x, the first step we need to do is section it. So I sectioned it. Let's call this section AA. But I sectioned it by keeping in mind that it's just an arbitrary distance x. Okay. So if my x-axis is defined here, then when I section it, I'm just saying, I'm not picking a specific location. I'm going to keep it general. I draw my free body diagram of that section, and I indicate all the forces that the section is subjected to. So I'm going to assume that there's a normal force that puts this member in tension, a shear force that puts this member in a clockwise rotation, and a moment that causes this member to bend in a concave fashion. So once I have my free body diagram, I can now write my equations of equilibrium that's only applicable from x greater than 0 to x less than or equal to 2 meters. So right up to here, right before that 5,000 newtons. So this free body diagram is valid from anywhere from here all the way up to right before point B. So I apply my equations of equilibrium, and I get the following. Sum of the forces in the x is 0. So that gives me n is equal to 0. Sum of the forces in the y is equal to 0. That gives me 2,500 minus v, that shear force, is equal to 0. So shear force is equal to 2,500 newtons. And this is only valid from x greater than 0, less than or equal to 2 meters. Sum of the moment must equal to 0. And I'm going to choose the moment to be at, I guess, this point. It doesn't matter where I choose it. So I'll just say it's at section AA. So this is my moment arm, which has a distance x. So that'll be moment arm x times 2,500. That'll give me a negative 2,500x plus this moment right there is equal to 0. So moment is equal to 2,500x. That is valid from x greater than 0 and less than or equal to 2 meters. So I have found how the shear force, the moment, as well as the normal force varies along the beam from A to B. We do the same thing now for the next section. So The next section would be right there from B to C. Here's A, B, and C. That would be 2,500 newtons, 2,500 newtons, and 5,000 newtons. And we want to section it some arbitrary location right there. And we'll call that section BB. And it'll be located a distance X. So once we section it, we have our section member, and we draw this 2,500 Newton force. We draw this external applied force of 5,000 newtons. And since we sectioned it, we expose the internal loading, and we say we'll have a normal force, and we'll assume that it's causing a tension on the member. We'll have a shear force, and we'll assume that it causes this part to rotate clockwise. And we have a moment reaction such that it causes this member to bend in a concave fashion. This is my free body diagram. So now I can apply my equations of equilibrium. So once I apply my equations of equilibrium, I have sum of the forces in the X is 0. That means N is equal to 0. Sum of the forces in the Y is 0. That would mean it's 2,500 minus V, the shear force, is equal to 0. And we can't forget that. Minus 5,000 is equal to 0. That gives me a value of V is equal to negative 2,500 newtons. And this is valid from X greater than 2 meters and less than or equal to 4 meters. So we do the same thing now. So now we do the sum of the moment must equal to 0. And we can choose any point. I can choose this point, or that point. I'm going to just choose this point A. So sum of the moment about point A is equal to 0. Therefore, I have this moment arm, which is 2 meters, and this moment arm, which is X. So that would give me 2 times 5,000. 2 times 5,000, that gives me a negative moment. X times the shear force V would give me a negative moment as well. So it would be Vx. And I have to add this moment. It's there. It's on my free body diagram. And it's positive. So that's equal to 0. Solve for the moment, because we know what the shear force is. That's just right there. We'll substitute it. So we have moment is equal to 10,000 plus the shear force of 2,500 X. And that would be in Newton meter. So we found how moment varies along X, and this expression is valid from 2 meters up to less than or equal to 4 meters. So the next requirement for this problem is they'd like for us to draw the graph V versus X and M versus X. So we already know from our previous calculation. So all we do now is just plot those on graph paper. So it's easiest if you, it's really nice to actually draw the beam, indicate the reactions, and draw the external force. And right below it, that's where we draw our shear and moment diagrams. I'll just say that's my shear axis, and it's in newtons, and this is my x-axis. And right below it, I'm going to draw my moment graph, where this is my moment, and it's in Newton meters, and this is my x-axis. So from 0 to 2 meters, I know my shear is 2,500 newtons, and it's constant, and that's valid all the way up to 2 meters. So I'll have something like that, where this is 2,500. And then the moment in that same region is 2,500x, meaning it's a linear function. When x is 0, so when x is 0, moment will be 0. And when x is 2, moment will be 5,000. So 0, and then it'll go up to 5,000. Shear is negative 2,500 in this region. So it actually is negative 2,500 from 2 meters all the way up to 4 meters. That should be 10,000. That should be 10,000. When x is 2 meters, moment is 5,000. When x is 4 meters, moment is 0. So that is our shear versus x, moment versus x. This is also known as our shear moment diagram.